Today we are going to show you an experiment about centrifuge modeling of geotextile reinforcement supporting a landfill lining system. And this was done by Pega and Tula from Michigan State University. It is popular nowadays to see vertical expansions of landfill due to limited space. Therefore, it's very important to analyze the deformation of the liner between those two landfills in order to minimize deformation. In this experiment, our objective is to use centrifuge modeling to demonstrate how reinforcement of the clay liner has been utilized to address settlement and stability problems in expansion of landfills. A geotechnical centrifuge can subject small models to centripetal accelerations which are many times greater than the Earth's gravitational acceleration. Acceleration level to test the unit weight of the soil being tested can be increased by the same proportion by which the model dimension have been reduced, and thus stress at the corresponding points in the model and prototype become identical. And here's the setup of our experiment, which had a camera inside the centrifuge machine to record all the videos. The hypothesis of our experiment is that reinforced liner can reduce settlement to a reasonable extent, and also we assumed that everything behaves elastically. The setup of our experiment is very similar to the vertical expansion of the landfill. As you can see, we have Ottawa sand on top, striform at the bottom, and that way we can observe the depression. Material we used are Ottawa sand, which represented the top landfill, striform peanuts, which represented the bottom landfill, plastic bag, which represented the plastic liner, and non-geotextile, which represented the reinforcement of the landfill. And this is the setup of our centrifuge modeling, and this was for unreinforced plastic liner. So you can see there's a plastic liner between sand and striform peanut, which acts as a liner. And here's the video which we did a flight of centrifuge modeling, and we went up to 40 G. And as you can see, we start from 1G, 5, 7, all the way to 40 G, and you can also observe the deformation as the G increases. Due to the speed of the equipment, it wasn't able to capture every picture at every G, but we can show you the maximum G it attained and also the maximum deformation we observed. This is the picture which shows the maximum deformation. As you can see, the red line which shows the deflection, and also we noticed a rupture at the plastic liner after we removed all the sand on top. So there was actually a failure for this one. And this is the setup of reinforced plastic liner. You can see there's a geotextile underneath the plastic liner. This is to make it more stronger. So now we're going to show you a video which will show how the deflection happens after reinforcing. So we started with 10G, 20G, and we went all the way to 80Gs. As you can see from the video, the deformation has already started to happen, and then at the end of 80G there was a maximum deformation, as you can see from the video. You can see the deformation on this slide by the red arrows. Although we went up to 80G for this flight, this deformation is actually less than what we measured without reinforcement at 40G. We also put a graph of comparison between what we calculated before doing the test and what we measured. In both reinforced and unreinforced, the calculated values are larger, mostly because of elastic behavior assumption. At the end, you can see in the graph, at a certain G, the settlement of reinforced is 3 times less, which is very consistent with our assumption.